All right, welcome everyone to the AF for Air Quality final presentations. Today we are joined to watch the results of our 10-week challenge. We worked very hard and we have some cool results to show you. So Barbara, I believe you created the short introduction for the team members in the challenge. So please take it away.
Yes, thank you, Dorian. So welcome everyone again to the final presentation. So over the past 10 weeks, this lovely group of participants have been working to create. The first aim was to create a deep learning model to detect plumes in the Greater Kampala area. But after research and a lot of discussions, the tasks changed for the different teams. So we ended up with 3 teams, where in team 1 and team 2, they focused on building a machine learning ops pipeline with hopefully a web application that could be integrated at the end. Then for team 3, they worked on deploying the plume detector that they had found. And then team 4 worked on source localization of the air quality data. So the first team will be team 3 that will give a presentation of their findings.
I will start then. Yes, so we started being more members in the team, but yeah, at the end, only few of us were more actively working on this. Antonella is the product owner, but she's not available today. And neither Ricardo, unfortunately. I think Michael should be around, and he will present the model development part. So I will start with the introduction of the problem statement and the data collection part. So, well, the problem statement was already presented. So the main goal of this challenge is to track plumes of NO2 and methane, which are 2 key pollutants over Kampala region using machine learning. So this is our roadmap. So we spent some time just looking at the data collection, using different tools, and but at the end we decided to use Google Earth Engine to retrieve the Sentinel-5. Then we all spent some more time just looking at the data, doing some validation of the images. And then in the meantime, in parallel, we work with machine learning application, looking at the model. And I will explain that later. And finally, we try to integrate the final, the workflow in a pipeline, and also investigate the model deployment. So yeah, some issues and limitations we faced during the challenge mostly was the data collection. Well, because I think it's one of the hardest part of this kind of challenge. It also requires a lot of time, also the data validation. And yes, so we decided to use Google Earth Engine because it's very powerful and it was somehow easier to retrieve the Sentinel images. And so for that, we start just defining the area of interest of Kampala region, Greater Kampala, and we download images for 2 years, the period of study. And we actually started collecting the NO2 column number density as the variable. And later we realized that we wanted to try with the tropospheric ozone which is the difference between these two variables is that the tropospheric NO2 is in the surface, while the NO2 column is just the NO2 over the whole, the different levels of the atmosphere. And after collecting the data for, all of the time step available, we decided to do some composites using just daily data. Some limitations of this approach is that we found a lot of missing values. And also in this area, there was a lot of clouds. And then for the application of machine learning, this is an important limitation. And so this is an example of using these two different variables, NO2 in the surface and using the other variable. We also realized that using NO2 in the surface, the number of missing values increased. But for the model, we actually try both. And I think now I should hand over Michael if he's around. I don't know if...
Yeah, I'm here. So I don't know, maybe cool. You can continue sharing, or should I share?
I can continue sharing, just, okay. Yeah.
Okay, so along the way, basically, it took some time to do what? To determine what the project goals were. But along the way, we decided that, okay, plume localization would be the what? Would be the end goal of the project. So basically, the first step was to do what? Was to detect the plume. However, we lacked labeled data. So research was made to determine what model could be used, like a model which has already been built to do what we want. And yeah, basically a repository called Plume Spotter, developed by Finch, was the one we went with. So Noella, can you continue?
Yeah.
So basically, we after the data had been collected, we tried to run inference on the images we had gotten. However, for the model which was in the repository, majority of the predictions were one-sided. That is to say, the model never predicted anything other than a class of 0. And as you can see here, it gave a predicted class of 0 with probability 100% to the class 0. So try to understand these results as much as we could, and we failed. So that's where the idea came to contact the owner of the repository, who was so kind to accept our request. And on discussing with him, we discovered that the model we were using, or the model in the repository, was very outdated, that he had updated it, but he had trained another model, but he forgot to update it. So yeah, he gave us an updated model. And if we can go to the next page, we can see that, yeah, there were beta variations. So basically here are extremes. Like, I picked out the extremes to explain why I came to observation that maybe a predicted class of 0 indicates like the presence of a plume, and the prediction class of 1 indicates the absence. So basically the image on the left, we can see that it's roughly 100%. Then the image on the right, it's 98% sure that there's no plume in that image. So from, at least from these results, we got some hope that the new model was working better, because there were some images which had like 50, 44, but yeah. So from here, we discovered that the model was working at least better than the one which was in the repository. So can we, okay. So we tried to see how exactly we could go about the deployment. This started at, like, we started this last week, and with Nick's help, I think from group 1, well, he provided a notebook which did majority of the work for us. However, there were some errors which took me some time to do it, to work around, because basically when the model is to be deployed to the endpoint, it's run in graph mode, and in graph mode, most of our preprocessing steps like are not supported. So I had to dig around that, but luckily, just yesterday I was able to fix it. So down here is a summary of the model because it's deployed once to the endpoint. So basically everything has to be there. So basically the preprocessing step has to be wrapped with the model itself. And also on top of that, since it's at an API endpoint, the data is not going to be sent. It's not going to be the way we were working with the full image. That is to say, it's going to be sent in serial pattern. So the input has to first be deserialized. Then after that, input it is run as input into the model. Then after that, the prediction is serialized and sent to the, I think, to the Google Earth platform. So because of lack of time, we only managed to like prepare the model because that was also some work to do. We didn't create an account because on top of that, there were some concerns that there would be costs incurred because at the end of the day, Vertex AI provides they provide that environment. I think they call it a node, and to use a node, you have to pay by the hour. So we were not sure if Airco was willing to incur these costs. So an account has not been created. So the model has not yet been deployed. And also because of time, because majority of people in the group have not worked with Vertex AI before. So no one had credentials, and yeah, no one was sure of how to make the credentials. So yeah, this is at least how far we have come. So yeah, to the last page. So these recommendations were made by Ricardo. He couldn't make it because he said he would be at work. But yeah, he suggested that ideally, if indeed Airco wishes to continue with this project, they would have to get a better understanding of the tropomic data because for us we had the lack of a masterclass really made it a little bit difficult to get going. Basically majority of the things were learnt like by the group because Ricardo said he had worked with Sentinel 2, 3, and 1, but he had never worked with 5P. Then also basically understanding the preprocessing. We talked to Finch and he was like, our preprocessing steps were okay. So yeah, I don't know about that one, but yeah, the other issue is that majority of the times the images we were downloading were highly affected by clouds, which kind of messed up the predictions. Basically, would have probabilities of none. And yeah, so we also suggested maybe getting some labeled data just to try some transfer learning, because obviously since we're just running inference, we're not really sure of the accuracy of the model because all we're doing is just like trying to understand the results. We're just taking the model as is, not really trying to tweak it in any way because obviously it was difficult to define what a plume is, and also to like get a very good working model would actually require a lot of data. So yeah, that failed. And lastly, basically Ricardo argued that downloading these average images required a lot of time. He would spend like a full weekend to get these images just in case they do what they decide to label their own data. So yeah, basically we are going to deliver the notebooks. I think the first one is the one which gets the data from Tropomi. Then the other one is the one which runs inference, and the last notebook is the one which is supposed to deploy to the API endpoint. The last one is complete. The only thing missing are the credentials, I think a region, an account, basically authentication itself. So yeah, that is team 3's presentation.
All right, thank you, Team 3. Thank you, Nulia. Thank you, Michael. Great presentation and great work. Indeed, good that you gave some advice in the end, some limitations throughout the project. Definitely some things that people from Airco can pick up if they decide to continue. So thank you all. And
hello everyone. So my name is Saloni and I'm from MLOps team. I'll be starting the presentation from our end, and we'll be discussing and about a brief discussion on the team and also about the challenge itself. I'll also speak a bit about ECO, and then I'll speak about the goals of the challenge. And then for further presentation, I'll be handing it over to Nick and Nanda. So let's start our presentation. And if you have any question, please feel free to ask. So as for team's introduction, we are a very small team. We have only 3 active members at the moment. And we all have one thing in common, that we are interested in AI and data. So we all wanted to work AI for good reasons, like across societies or other organizations. We are placed in different part of the world, and we worked on this challenge with with many different things, new things, and we explored many new things. For example, Google Earth Engine and other things. Initially, we started working on on methane data to explore the plumes, but in the after few weeks discussion, we were like aligned for MLOps and started working on the MLOps deployment thing. So I'll give a brief introduction about the challenge. So AI for Air Quality Challenge is it started on 28th of June on Food Crunch AI platform. It was a collaboration between group of AI volunteers and AirCo. It's a very interesting challenge where we are trying to look into the air quality and trying to predict the air pollution across African societies. The points that I was interested about AirCo when I was doing a bit research on like how AirCo was founded and what are the grounds they hold is like AirCo was founded in 2015 at Macquarie University, and their vision is to have clean air across all the African societies. The most interesting thing about AirCo is they don't have an infrastructure to support expensive air sensors, so they build their own air sensors and place across different parts of the Africa, the whole continent. And they are targeting to do like collect huge amount of data, and they are trying to look into the air pollution and how they can reduce those air pollution, and also trying to aware people across African society to overcome those air quality issues. So the challenge, this air quality challenge, they like trying to introduce across the Fruit Punch AI platform is just to use the deep learning models to get more insights and to provide help to the people across the African society. So I'll speak about the goals for the challenge. So the goals initially we had decided with main goal was to build a DL model, deep learning model, to analyze the plumes and sources across the Kampala region in Uganda. And with that, the sub goals were we are going to use the Tropomi data and then create a deep learning model to detect those plume and hotspots, and then do a time lapse map. But after a few weeks discussion, we were ended up with some hiccups. So we had a discussion and we decided to go with the Finch model that was already there. So we were using the CNN model, which Team 3 already shown in the first presentation. So that's the aim. We use that, and as part of MLOps team, what we are trying to do is we are going to use that Finch CNN model and deploy that at Vertex AI, and then that Vertex AI deployment we are going to integrate in Google Earth Engine. So that's the refined goals we have set for our team. Now I'll be handing it over to Nick. Thank you.
Thanks, Silani. So I guess the project timeline, Team 3 did a good job of outlining that in their presentation, so I'll just gloss over it. Kind of in the first 6 weeks, we're looking at the literature and kind of, I guess the project scope was still being finalized in that sense. And in week 6, we managed to resolve the project scope and the different team responsibilities. So the team splits ended up being teams 1 and 2 would be working on the MLOps platform. So team 1 and 2, that's us. the plume detection model with team 3, and then source localization model with team 4. So I guess detecting the plumes and then the source localization kind of looking within those plumes where the emitters would be from, and then the MLOps platform kind of tying everything together through the data ingestion and kind of running these models and then making these results available to a user-friendly interface. And I guess when we're looking as a team at what sort of solutions there are in terms of MLOps, I think there are quite a few options. But I think when we I think the best option really was Google Earth Engine. And for those who don't know what Google Earth Engine is a it's a platform run by Google for petascale geospatial analysis. So when Google Earth Engine, I mean, it's a bit of a confusing name. You have Google Earth, which is the desktop application for looking at satellite data. And then you have Google Earth Engine, which is this very large platform. And basically, the principle behind it is the co-location of computational resources and the data as well. So when we look at these sort of geospatial applications, since the data transfer is since the data sets being used is they're so large, doing these sorts of processing on a local machine is just bottlenecked by your network and as well as your computational resources that you have in your machine. So by co-locating the computational resources as well as the data in the same place in Google's data centers, we're able to do these computations much quicker. And yeah, that's pretty much it. So we're able to do large computations very quickly. So yeah, the data sets provided within the Google Earth Engine platform are very extensive, providing data sets from many different satellites, including the Tripome sensors on the Sentinel 5P satellite. And yeah, in order to interact with the Google Earth Engine platform, there is a browser-based IDE as well as an API to interact with that. So that's a JavaScript API. So JavaScript is the browser-based IDE, but you're also able to interact with it using Python through the Earth Engine package. And you can do that in a Jupyter notebook locally. And basically, it'll bundle the code that you write and actually deploy it on that platform. It'll run it server-side on Google Earth Engine servers. The benefits of Google Earth Engine for this project is that Google Earth Engine is actually free for non-commercial use cases, which is great for us because this is a non-commercial use case and is an impactful project. It is the industry standard when we look at these sort of large-scale geospatial applications, geospatial analyses. There is minimal code and configuration. You can imagine since Google Earth Engine and actually something I didn't mention as well is there's also Google Earth Engine apps as well, which provides this dashboard interface to run these analyses. So you can actually query, you can actually interact with that as a user. The minimal code and configuration, it handles the data ingestion, the computation, as well as the dashboarding. That's all taken care of, as well as the scaling up and down of computational resources. So it's a bit of an all-in-one solution. And what really, another thing as well is it opens a possibility for us to actually leverage open source applications to cover more ground. So we're able to adapt existing dashboards that are open sourced and use those as kind of a starting point for us to kind of get started with Google Earth Engine. So that's what we went ahead and did. And one of the interesting dashboards that's available is the Tripome Explorer. So this application is open sourced by the original creator is Google. So I think yeah, it's Google. It's created by Justin Drayton, I think. Yeah, Justin Barton. But yes, I guess within what is effectively 1,500 lines of code, which most of it is configuration, they created this application to view all these different features here from the Tripomi data sets. So we're looking at adapting this and then integrating it with Vertex AI. So kind of looking at the Kampala region specifically, and then being able to segment data from the Kampala region, batch it up, and then send it off Google Earth Engine to run predictions within Google Cloud, and then get those predictions back and display them within Google Earth Engine. Google Earth Engine has native support for some machine learning models. So basically within the JavaScript API, you can create some regression models or some classification models on a per pixel basis. But for running convolutional neural networks like we're interested in, you need to actually do those predictions off platform on Vertex AI. And that's actually where the cost comes in for those off platform predictions. Since Vertex AI is a cloud service managed by Google, there is that associated cost. Unfortunately, that was one of the major stumbling blocks that we came across. Just the startup of actually setting that up, setting up the cloud accounts and getting that model actually deployed to Vertex AI was one of our difficulties. So we weren't able to really progress into like the actual dispatching of these like requests of these predictions and the visualization within the dashboard. So that's a bit unfortunate there, but I guess that's where we are at the moment. Yeah, I'll hand over to Nanda now to take it away for the rest of the presentation.
Okay. Thank you, Nick. Okay, is my voice clear? I think it's clear. Okay. So moving forward, for the MLOps team that we have our struggles. So can move forward. Okay. So we have our own struggles. Mainly, the struggles are in the volunteers schedule and engagement, and also the data set. For the for the volunteer itself, we came from a lot of time zones, which makes it very hard to schedule meetings to discuss a lot of things, and it is the earliest bottleneck we face. But because of that, I believe that not many people are engaged. This was a problem in both team one and team two. So the situation is that team one and team two are having a very few active volunteers, few engaged volunteers. So in the end, we decided to merge up. But even though we already merged up, we still end up with not many people left. We only have three right now, but before that we had team from team one and two combined around 10 to 15, if I'm not mistaken. But we only have three now. And yes, the project scope were changing from the beginning, and it is very difficult to keep up because the volunteers were also based on a different time zones, and also the data set is most of the times in the group discussion or the whole team discussion, team one, two, three, and four, we're mostly discussing about the data set itself, the source of data, and how do we collect the data, how do we process and pre-process the data before we feed into the machine learning model. It's so unclear, and most of the efforts, around 60 to 80%, were mostly focused towards it instead of building the models and focusing on the solution. So that is the MLOps team struggles. We can move on to the next slide for the future works. Okay, thank you. So I believe that the future work, as Nick already mentioned, is to work on about the Google Vertex AI because it's hard to use CNN on the Google Earth Engine right now. It's better suited for the Google Vertex AI, and exploring it will be much more beneficial to the ERCO's current tech stack because because when ERCO explained to us the tech stack, they utilize a lot of Google Cloud platform. So as the Vertex AI is already integrated into the Google Cloud platform, it would be very beneficial to the ERCO's current tech stack. So they don't have to adapt to a whole new tech stack again. And this, from us, this was totally worth noting for. So I believe that's the end of the MLOps team presentation. So thank you everyone for listening, and please do ask us if you have questions. Thank you.
All right. Thank you, Nanda, Nick, Saloni, for the presentation. Looking well. So maybe question, how far did we get with adjusting the Tromponi Explorer for the Kampala region?
Yep, I'm happy to answer that. I'll basically the extent to which we got was to highlight the Kampala region, clip the data, as well as define some a buffer around the Kampala region, because I guess it's like we're not interested. I guess we're not strictly interested in like everything just within the boundary, if that makes sense. If we're also interested in, I guess, a square rectangular region around it. So just kind of creating that buffering and clipping that data. I guess beyond that, we also do have the code necessary in order to integrate it with the Vertex AI model. It's just that that endpoint wasn't there, so it's actually that isn't included in the script that we wrote, the Earth Engine script. But yeah, the clipping and the actual like loading of that shapefile is managed.
All right. Thank you. Any other questions?
Yeah, hi everyone. So my question, I think, is for the first group that presented. I'm not sure if they're still here. So you did mention you use, okay, I'm just trying to understand the data. I think the last time we left had shared data, but if I'm correct, you're using Google Earth Engine. So if you are planning to use, say, the application in real time, are you able to stream data in real time using the platform that you used? So say I want to use this application for 2023, do I have to go back and download this data, or can I just have sort of an API that streams the data?
Yeah, I'm happy to answer that question. So when we look at Google Earth Engine, my understanding at least is that as you're kind of interacting with that interface, you're able to, as you kind of browse this data, you can get those, whatever data you browse to, you can get those predictions dispatched. So that data is, I guess, that's displayed within the Google Earth Engine interface, and then that can be partitioned and dispatched to Vertex AI to run those predictions, to identify those plumes, with those predictions being sent back and stored. So when we look at the Tropomi data set, we have both so there's two types of data that we have, which is the near real-time data and the delayed mode data. The delayed mode data being higher quality, but being delayed because they do QA/QC on that. So that might be out of date. So I guess our main interest is the near real-time data, which to my understanding is available a few hours after flyover. So the data availability is pretty much real-time, and there is no downloading of data because it's all managed server side on Google Earth Engine. That's the hypothetical. I guess that integration of actually getting the Vertex AI platform talking to Google Earth Engine. We didn't actually manage to do. But I do think that Google Earth Engine as a source is very valuable, especially for this large-scale geospatial processing. And I think it would be really good for AirQuote to kind of pursue that avenue of using Google Earth Engine in general. Hopefully that provides insight to your question, Priscilla.
Yes, yes, it does. Thanks. I guess we'll have to look into that as well.
All right. Thank you for your question. That brings us to team 4, who has been focusing on source localization for the last couple of weeks. So I'm curious to hear how that ended.
Great. Okay. So indeed, we have been focusing on the Plume source localization. Well, first of all, we did not use the fruit punch format. I saw everyone else did it in their slides, so apologies for that. We did not get the memo. But yeah, we assume when making the slides that there would be at least another team introducing the problem itself. We're very happy to see that that was indeed correct. So we can jump directly to what we've been focusing on. So indeed, as you can see, there were essentially 3 main components. There was a plume detection model, there was the MLOps part, and the plume source identification. There is also the component of the visualization, but due to time constraints, none of the teams, from what I hear, we had time to work on that. So we're going to just tell you a bit about how we approached this plume source identification, and what we did, where we're at, and what is maybe some future work to do as well. First thing is basically the purpose of this. So the idea is that given a plume photo, a plume satellite image, like the one on the left, we are able to pinpoint where it is coming from. So essentially from the ground, where would it be exactly coming from? And with that information, provide a possible or likely source for that plume. So that could be, for example, a highway, that could be a power plant, there could be several sources. Also good to mention, the photo that you are seeing is not from our work, is actually a study by Beerley et al., several people that already work on pinpointing nitrogen oxide emissions from space. So they worked exactly on what we are interested in doing. There's how we did this, our approach. There's 3 main things that we had to do, or 3 main components. On one hand, we wanted to combine the satellite data, so this would be the plume images, with wind data, because NO2, of course, is dispersed by the wind. So we wanted to take into account the wind direction and wind speed to see how these plumes are moving. Essentially, the second thing that we had is create a list of the possible sources. So as I mentioned before, this could be, for example, highways or power plants, but we wanted to do some research and provide a more exhaustive and thorough list of possible sources of the emissions. And finally, the pinpointing itself. So that would be like the image you just saw before, finding exactly where these plumes are being originated, where they're coming from. And for this last part, we will be leveraging the work we just mentioned, because as I said, like they're essentially doing what we're trying to do. So we thought it would be smart to try and replicate part of the work. And without further ado, we go into the actual approach step by step. So I will give in the microphone to Feline, as she's going to tell us about how we obtained and combined the wind and satellite data.
Yes, thank you, Sarah. So we did manage to obtain the wind data and to combine it with the plume data. So for the wind data, first we looked into using the data directly from the Google Earth Engine, but that didn't work out for us. And then we asked AirQuote, and research facilitated us with the data we needed from a ground monitor in Kampala, which has both the desired frequency and information like this wind speed and the direction in 1-hour intervals. And we use, like, based on the overpass time, like a certain amount of hourly intervals from this wind data. So that was very nice that we got that. And then for the satellite data, like the general idea is that we
You're muted, Fabina. Something happened.
Yes. You hear me again?
Yes.
Okay, I'm sorry for that. Then for the satellite data, the general idea is that team 3, who created the plume detection model, provides us basically with an image which is a plume, or the plume detection model does that. So as an input, we have an image of the plume, like an NO2 image, and we also need the exact date and overpass time of when that satellite image is made, because then we can select the relevant wind data. So we do get the date at the moment, but last time I checked, we didn't have the exact time of the image, so that's still an open request. For now, we just assume that it's 10:30 UTC, because that's around the time that the satellite passes over each day.
Oh, sorry, did I go too fast? You want to say something else?
Yeah.
Okay, so Rafael, yeah, he's going to present this.
Okay, so I thought Flynn was still going to talk. As Sarah has already said, the primary source of NO2 is vehicles and industrial processes. So for this, we were looking for the places in Kampala where there can be possible NO2 sources. So for this, we created a GeoJSON that uses 3 geometry types. So we have a polygon that has the industrial area that covers the industrial area of Kampala. We have line strings that have the highways of Kampala. For the highways, we found a data set that contains all the roads of Uganda, and then we filtered by the highways and for the area of Greater Kampala. And we also have some points that include some power generation facilities and the Kampala port. This data will be merged with the results, so we can get a general idea of potential sources of the plumes. Now I'm going to hand over to Mies to explain the next slide.
Yes, thanks, Rafael. So as Sarah mentioned, we used the work of Berle et al. As an inspiration for our localization of the NO2 plumes. And it uses a combination of the wind speed and direction and the satellite data. And so the equation is basically 2 parts. That's the S and the D part. So the S is the sink of NO2. Over time, NO2 reacts with the environment and then it gets lost. And the D stands for the wind. It's a flux for incoming and outgoing NO2. And you can calculate it with the wind. And due to time constraints, we haven't looked yet to the sink, but only used the wind. The wind part of the formula. And I forgot who's going to do the next slide.
If I may just add one last thing, Mace, to what you said. There's also part of the formula that we're not using. You might notice there's an L and a tau there. Both of those values have to be determined empirically through experimentation, through exhaustive experimentation. There's no, or at least the work that we are leveraging, they didn't find any better way to do this. So because we don't have time to actually do exhaustive experimentation, we're also not using those values. We also consider using the same values that they're using, but they were focused on a completely different area in the world. So we didn't think it would be applicable. We thought it might actually be a bit risky. And that is why that is also being left out in our approach. And the next slide is me, actually. So this is a roadmap, an updated roadmap. We already presented in the midterm presentation of what we were going to do. But just to give an idea of how far we are and where it still has to be done. So we already, as explained, collected all the input data, so the satellite and wind data. We have also done all of the research in the possible sources, and we have all of the location files. And we are now busy with the model itself. So we have been able to combine the wind satellite data with all the shifting images. So we now have basically one vector that has both components, and that would be also the formula you just saw. And we are still busy. What we have to do next is combine those images, so the satellite image with the wind data, with the geolocated sources. So basically the three inputs that we have all combined in one. And then finally apply the actual model. So that would be basically finding the closest possible source and suggesting that as the pollution source. And that's what we're busy with right now. So we don't yet have the model that provides the source, but we have an approach as we have defined. And I believe Feline and Rafael are going to explain a bit further about our current state.
Yes, thanks. Yes, so where we are now is we are able to overlay the satellite images with the sources. We're also able to shift the NO2 plumes based on the wind data, but we're still lacking a method to automatically select the potential source. So that's what we're going to be working on next week. And there's one thing that we have been struggling with a bit for now. Maybe like the team working on the MLOps has some suggestions on that. So what we did now, we transformed satellite images into the NumPy arrays in order to do the calculations on the data. And then we created from that NumPy array the shifted satellite image. Yeah, that's why we also still need the overpass time. So we select the accurate wind data. Sometimes it's 1030, but I also saw values up to 1140, I think. So that's still 1 hour difference. Yeah, and we are currently working on applying the model on getting this combined and combining it with the sources. Yes, like we mentioned previously already, we do not take into account the NO2 sinks for now. So basically our plume stays as it is at the moment of detection, and it just shifts, which is a very simplified version, but we assume we can use it to at least get to the potential source. Yeah, and it might be valuable to use that in future work. And here in the picture, you can see an example of the overlay of the images. Rafael, do you want to explain what we're looking at?
Yes. So I believe the white squares are the higher concentrations of NO2, and the darker ones are the missing data, as we can see on the legend. So the blue points are the sum of the possible sources, such as power generating facilities. We can see the roads, the line strings, and well, the industrial area is harder to see, but it's very close to the letters ALA of Kampala. So here we can, well, kind of identify potential sources. Maybe we can change the legend to potential NO2 sources, so it's not like, okay, it's there. And I think that's it.
Yeah, that's it for team 4. We also did not include a slide with the struggles, but very similar to other teams, also aligning the time for all the volunteers. We did have quite an engaged team, so that's quite nice. But yeah, that's it for us. Any questions?
All right, thank you. Thank you so much, guys. Good presentation, and you did get pretty far with the limited time that we had in the second half of the challenge. I had a question. Considering like the plumes that we see are covering quite a large area in the image. So I believe that one pixel was like 7 by 7 kilometers or something. how well do you think you can actually pinpoint the certain factory, or let's say certain highway, that is causing, or at least causing a large part of the plume?
Well, it's probably not perfect, of course. And well, as we mentioned, there should be more research and more work done, especially in identifying what time frame and so the variables that we didn't include. I think we are leveraging work that is using exactly the same type of satellite data, and they were able to predict quite accurately which was the location. So I think actually our biggest limitation is more time constraints. With proper time, I think you would be able to have a relatively accurate idea of where it's coming from. That being said, of course, there's a risk, and also because we only get one satellite image per day, we also can be missing a lot of information. So the answer is we're not entirely sure because we don't have time to provide a very accurate answer, but we believe it's possible to have quite an accurate, good result.
All right.
Can I still add something to that? I agree that like with certain timeframes, we will be able to find the source. But then last week I found this one article by NASA, and they showed, I think it was also plume detection or NO2 values, and they had data, I think, from like each hour. And you could really see that during a day it could shift. So I think it's one thing to be aware of. If we detect a plume, then I guess we should be able to find the source, unless it's of course already spread it out too much over time. But there's also a big risk of missing plumes, because if it arises in the evening, then it could be that it's not there anymore by the time that the satellite makes the image.
Yeah. Okay. Do you think that enlarged, because now we're focusing on Kampala only, and I see the research that you showed in the beginning of the slides was, I believe, from a large part of South Africa, where you had Johannesburg, Pretoria, and those are very large cities, like I think as big as Kampala. So would it work better if you take a larger area, so like maybe whole Uganda, or what would you think the model will do?
Well, that is a good question, because indeed the photo we showed is from South Africa, but the interesting thing is they actually developed the model for Riyadh, the capital of Saudi Arabia, and then they used it on South Africa and Germany. So these are very different sites to look at, and the model they developed works for all of them. So I would think that the area itself wouldn't affect, at least if what the results they are presenting are, of course, true, and they're not just.
All right.
And it might, well, I guess it also depends on what level of source localization you want. Do you want to know the exact factory, or do you want to know the city where it comes from?
Yeah.
So, yeah.
Okay. Very nice. Any other questions?
Well, maybe I have a question then. I also mentioned it in the presentation. It's, I think for team 1 and 2, do you think it's possible to apply calculations on the NO2 satellite image within Google Earth Engine, or maybe some other way without extracting the NumPy array first? Because that's really bothering me that we need to do that.
Yeah, within Google Earth Engine, you can work individually with the layers, so combining them in different ways on a per pixel basis. So I think a lot of the source localization can also be transferred into Google Earth Engine, the logic as well.
But is it possible to do calculation based on a specific layer?
Yes. Yeah. I think you're able to. Yeah, you're able to request the different layers and stuff like that. Yeah.
Then that might be a potential solution.
Yeah.
Okay, thanks.
All right. Yeah, I think that brings us, if there are no more questions, I think that brings us to the end of the final presentations. The teams have 1 more week to round up all the code they're working on right now and finishing their reports. I will also be creating some peer reviews that will help me in creating your certificates later this week. Peer review takes about 5 to 10 minutes to fill in for your team, and based on it, we decide which skill badges you receive on your certificate. That's what you will receive later. But I think for today, I just want to really thank you all for your hard work. I know that we have had some serious hurdles to overcome, some unclarity at the beginning of the challenge, but I believe that once we came up with a good game plan, you guys really pulled through. So thank you all very much for working with us. And I really enjoyed the challenge, and I really love to see the results. I'm looking forward to read the reports. And maybe I want to give the final words to Barbara and Priscilla, and then we can round off the challenge.
Yeah, thank you guys so much for participating in this challenge. Yes, it's been a journey, but I'm happy with the results. Yes, and then Sasha from ERCO, she requested that she'll create like a Google form with some questions where they wanted to write a blog post about your experience in the challenge. So when she does that, I'll share it with you guys, and feel free to give your experience and any tips and stuff. Yeah. But thank you again. Thank you very much. Yeah. Priscilla?
Thanks, Barbara and Dorian. I'll just add to your voice. Thank you, everyone, so much for powering through the challenges. I think it is not unusual to come across challenges when you're working on a scientific project, I guess. So the idea is always to find a solution as you go. And apologies for that. If there was some bit of lack of clarity in the beginning. Yeah, of course, this will be a learning for us. Maybe next time we'll have like maybe a simpler challenge or something like that. Thank you so much all, and I look forward to the outputs. We will find a way to sort of consolidate and maybe improve where necessary, where you couldn't complete because of, say, time. And yeah, Richard also sends, I think he's unable to make it because he's attending a conference in Ghana, so that's why he's not here. But yeah, thank you so much and have a nice week.
All right, thank you all, and have a very fruitful evening. I'll talk to you later. Ciao, ciao.
Bye.
Thanks. Bye.
Thank you.